Hi, I want to make a shunt. I said shunt! I want to make a shunt current sense resistor. Basically, the way we measure current is by converting it into voltage, passing it through a known resistor, which we call a shunt. And so the current is the measured voltage divided by the known resistance. To measure the current accurately, you need a relatively accurate shunt resistor. For example, here I have a 1 ohm 5% resistor and I'm going to run 2 amp through it and measure the voltage across it. See, now the voltage reading here is actually showing that there is 1.8 amp running through it. It's burning now. Of course, that means 4 watts of power that burns my resistor. You can buy higher power shunts that are made for this purpose. But why pay so much when you can make a relatively accurate shunt yourself? You just need some length of wire. Every wire has a known resistance. If you search Wikipedia for AWG or American wire gauge, you will find a table showing information for every wire size, such as its resistance per length and diameter and such. And of course there are other standards too, like British standard wire gauge. So basically, using a shunt resistor, you are generating a voltage drop that's not very desirable. Why? Because then you are dropping your supply voltage level by that much, which will affect the current running through the load. But if you keep that voltage drop small or compensate for it by increasing the supply voltage, then you're fine. I like to keep my shunt maximum voltage small. To start, I like to have only 100 millivolts for a maximum of 1 amp, which means around 100 milliohms. Regular multimeters are no good to measure such low resistances, but they can measure voltage and current much more accurately. What I have here is a 22 gauge wire, which is around 53 milliohms per meter, and so I would need around 2 meters of this wire. Now I set my power supply to output 1 amp accurately, and I run the 1 amp of current through my 2 meter length of wire, and I measure the voltage across it. And I have to read 100 millivolts, but you see I'm reading a bit off. So I stripped some length of wire and I'm gonna slide my probe across it. And you see, as I slide, the voltage starts dropping. I'll keep going until I get exactly 100 millivolts, right there. This means that to have exactly 100 milliohms, I have to measure exactly between these two probe points. So I mark them. I'll solder wires to the 2 spots I marked on my shunt wire, and I measure the voltage between these 2 wires. The length of the measurement wire is not important because there is no current running through it. Now I'll wind my wire like this so it takes less space. This is bad because I'm making an inductor. If I try to measure higher frequency AC spikes or transients, this will filter them. It's easy to solve though. First I bend the wire at the center and then I wind it like this. This will remove the inductance. You think I'm joking? No. If I bend the wire like this and send the current in, on the top wire it creates fields like this, and when it returns on the bottom wire it creates fields the opposite way, and the fields cancel each other, so no inductance is created. Elementary. So here's the shunt. Now let's do a comparison between readings of the supply's ammeter and our shunt. Who set everything at maximum? I guess I did. What can I say? I like extreme shit. So here we are. I set the current to 100 milliamps and you can see that the supply can't show it accurately, but the shunt can. That 10 millivolt voltage times 10 is the current running through the shunt, which is 100 milliamps. And if I change the current, our reading is still pretty accurate. I like to be able to measure higher currents, like 10 amps. But using this, the voltage drop would be 1 volt, which is too high for lower supply voltages. So in order to get the same 100 millivolt drop, I have to change the resistance of my shunt to 10 milliohms. It's simple. I can still use the same shunt and just inject the current and read it at 1/10 length of this wire. Let's just see if it can handle 10 amps or it will burn. I'll run 10 amp through a short piece and see if it gets warm. No. See, the mouth and the lip area is more sensitive to heat. It's slowly getting warm, but it's not too bad, so it should be fine. And if you're wondering how I'm running 10 amps through my mouth without dying, there is no current running through my body because the voltage across my body is 0, so the entire 10 amp is running through the wire. First, I strip this wire at 1/10 of the length with some margin for calibration, which is around 182 millimeters in this case. Then I solder a wire here, and that's where I'll inject my 10 amp current. Now I'm running 10 amps through my wire and have to see exactly at which point I'll read exactly 100 millivolts, which is right around here, and I'll mark it. And I solder my measuring wire to that spot. And this time, to get rid of inductance, instead of winding it, I'll just fold the wires side by side. Something like this, and now we can tape it together in a bundle and label the wire so we know which one is for which. And also don't short the bare wires inside the shunt, otherwise it will change the resistance and throws your reading off. Now let's step up the game. I want to be able to measure up to 100 amps, but my supply here can't output more than 10 amps. So I'm going to use my auto transformer that can output some high AC currents. I have a piece of 22 gauge wire here which I'll measure the voltage across. If I connect it to the output of my auto transformer, I should... and burn my fingers again. The piece of wire simply shorts the AC output, so I start at 0 volt and slowly raise the voltage while I'm measuring the current with my clamp meter. Let's see. Oh, I'm starting to think coming up with the idea of a light bulb didn't require much genius. In fact, the dumber you are, the more likely you are to invent a light bulb. And remember, if your shunt gets too hot, its resistance rises so much that its current reading won't be accurate anymore. We definitely need thicker wire. I have this 18 gauge wire which is around 21 milliohms per meter. So for 100 amps and 0.1 volt drop, I would need around 4.75 centimeters of this. Okay, let's see if it can do the 100 amp now. There. 77. Ooh, starting to smoke. Come on. 80. Oh, melted again. We need thickness. Unfortunately, I'm in luck. I have some 8 gauge wire, which is around 2.1 milliohm per meter. So I would need around half a meter of this for 1 milliohm or 0.1 volt per 100 amps. If this can't do 100 amp, nothing can. There we go. Let's see. There we go, 100 amps. And it's holding on pretty... Oh, my auto transformer can't take that much power. So I can't calibrate at 100 amps because my auto transformer blows up. Anyways, I don't really trust these current clamp multimeters because they're fine, but they are not very precise. I'm thinking just to calibrate the length of this wire at 10 amps using my precision multimeter, which will give me enough resolution, and then I can use this up to 100 amps. There we go, I'm running 10 amps through the wire, and I'll be looking for 10 millivolts exactly. Right around there. Now let's do a comparison between the clamp current meter and my shunt. Of course, I trust my shunt a bit more. Just remember that whatever voltage you read there in millivolts times 1000 is the current. Okay, let's do it. There, 50 amps, 47, 48. Well, actually the clamp is not very bad either. Ooh, it seems like the current is rising. Oh, because the auto transformer is burning. There, now we have a precise 100 amp shunt resistor. Now some of you might ask, why don't I just use a multimeter or a clamp current meter to measure current? No, that's fine, there are no stupid questions. 3 reasons. One is that the current might be outside the range of your multimeter. For example, if I want to measure 10 microamps, I have to use a shunt of around 10 kiloohms and measure 100 millivolt across it. In that case, I can measure accurately down to nanoamps. Secondly, clamp current meters are fine, especially since you don't have to cut through your contacts and you just clamp around them. But they are not very accurate at low currents and their precision can be as bad as 5 to 10%, where a shunt can easily be as accurate as 1%. Third, and most importantly, the meters only measure DC and RMS. But with a shunt, you can connect it to a scope and see all the current waveforms and transients. I have an example set up here. I have my 100 milliohm shunt resistor I made in series with the primary of my microwave transformer, and there is no load on it. And I'm gonna measure the voltage and current of the AC line on my scope. Let's see. You can clearly see that the yellow current line is leading the voltage green line, as should happen in an inductor. But why the f the current is not a sine wave? There, it says the current should look like that if you are using an iron core, because the iron core doesn't have a linear magnetization. The you see and learn using a shunt.
Giveaway time!
Thanks to Circuit Specialists for providing the essential tools I need to make my videos. They will provide 5 of these awesome LCR meters and 5 of these USB oscilloscopes to my viewers and patrons. I mean, their website is filled with these great low-cost tools that you can buy, like this thing that you just plug your component into, and it will tell you that yes, it's an NPN transistor and here are the parameters. As usual, the patrons are automatically in the draw, but for the viewers, if you need these tools, please leave a comment under the video like the usual, give me the meter!